Hi, welcome to Lab 5 for Physics 2211. Today we will be going over the Choose Your Own Adventure Slinky motion. In this lab, we will discuss the purpose and a preview of the results, the physics principles with an analysis in the context of the lab. Furthermore, we will explain the ideas and the principles used. Then we will put the data into Tracker and GlowScript, comparing the results, and we will form a conclusion on those results and comparisons. In this lab, we will observe and compare the predicted model with our observed motion of the slinky using Tracker and GlowScript. We will see changes in potential energy, gravitational potential energy, spring potential energy, and total energy. Here is a preview of those results on the side using the graph. Some of the important forces that we will discuss include Newton's second law, the energy principle, gravitational force, drag, and tension. The energy principle states that energy can either be destroyed or created, which is apparent in this formula. Newton's second law affirms that the motion will remain in motion unless acted on by an outside force. Gravitational force pulls objects with mass towards each other, in our case, our system. Relevant formulas include the work done formula, the spring motion, the gravitational energy formula, F net, and velocity update formula, including the momentum update formula. Here is the tracker analysis, and as you can see, we have the two graphs next to it. There is the x position along with time and the y position along with time with the center of mass coordinates and the center of motion coordinates. We see a pretty linear path for the descent of the slinky once it gets to the certain point where all of the slinky is in the same spot after it's dropped. And here is the code with the initial conditions taken from Tracker. As you can see, we have the mass as an estimate of the slinky's mass. The initial position is also given from Tracker from the coordinates that we got. G is the gravitational constant, B is the estimated drag force, which we have as 2.6, and the j hat vector, again, is that position. Looking further at some of the code here, we have the while loop, which is used as the calculation loop for the predicted motion and visualization of our path. And we use the velocity update formula along with the position update formula. And we have another while loop, and here we have to find the drag force, the net force, the position update, and the velocity update. So we use the momentum principle for that, and we also use the drag equation to get the FD here. Here's the full analysis where all of our position points are put into a graph comparing them. So as we can see, we have our tracker data differs from our GlowScript data, which is evident in the graph here. This is because real life does not always follow the same motion and conditions as a simulation model, as in GlowScript. So we have to take this into account when we are accounting for all of our forces and such. What does this data mean? So we can conclude, based on our slinky, that it does stay in place, satisfying the second law of motion for this experiment. We have seen the rest of the slinky from the bottom cause the rest of it to fall only when it has traveled to the center of mass. The second question is, were we accounting for all the forces in our tracker model? So here I chose to define the system as Earth and the slinky and everything else in the surroundings. We can see how there are differences in my computational model and the real-life model. So this means that all of the forces were not accounted for in our computational model. This could be due to experimental errors or not accounting for the force of the hand dropping the slinky in the original video. Some experimental errors that could have occurred during this lab are misentered numbers, rounding errors in determining the center of mass and the point of mass, and misinputted tracking points for the tracker points. A conclusion we can form from this experiment is that real-life scenarios don't always match computational models. This is true as it is hard to find an ideal situation where the conditions match ideal reality. We would have to have a certain set of standards and initial conditions to match our computational model in GlowScript.